All right, Algebra 2, Lesson 57. We're going to talk about finding exponential growth and decay. There's a lot to this. There's really not that many slides, but there is a lot to this. Exponential functions can represent many real-life situations. A function is increasing if its output increases as its input value increases. So if we're looking at a graph, right, as we get further to the right, it's going to increase exponentially. Okay, so as this number increases, this number increases. Does that make sense? Okay, that's exponential growth. Its graph rises from left to right. Exponential growth functions are increasing functions used to model situations where quantity is always increasing by the same percent for a given time period. It's modeled down here, but let's try to think about things that have exponential growth. What types of things have exponential growth? Flowers have exponential. So let's be a little bit more general, and let's say populations sometimes have exponential growth, and usually sometimes like the smaller the life form, like say bacteria, have higher exponential growth rates. You could probably look at, and people like to say that human population is exponential. It's really not, but it's more complicated than that. What? Oh, the census. Talking about the census. Yeah, they do that. They do the census every 10 years and kind of see how that thing maps out. The thing is, with like human population, it kind of goes like that. Like it will have periods of exponential growth, and then it will level out until something changes, and then it'll shoot up again, and then it'll level out. Right, and it'll do some things like that. Of course, you look at human history, it's not always been that way because, you have like the Dark Ages and the bubonic plague takes out a third of the population. Okay, not exactly exponential growth at that point. Let's see. Okay, so we have functions for this, and our function is f of x, or y, it's the same thing, equals our constant times b to the power of x, where k has to be a number greater than 0. Okay, can't be a negative. Basically, what we're saying there, it can't be 0, and it can't be a number less than 0, so it can't be a negative number and still be exponential growth. Okay, and let's see, and b has to be a number greater than 1. Okay. So that's why that is underlined and bolded down there. So how can I tell if I'm dealing with exponential growth? If my values that represent k and my value that represents b fit those qualifications. Does that make sense? So you might want to refer back to this deal here, either in your notes or in your book. All right. Let's keep moving forward. A function is decreasing if its output value decreases as its input value increases, meaning that if I were to look at a chart of this, right, I might see something that looks like that, okay? Meaning that as this value down here, which is my x values, which are my inputs, right, as those increase, my y values are decreasing, okay? Its graph falls from left to right. Exponential functions that are decreasing model exponential decay. Exponential decay is used to model situations where quantity is always decreasing by the same percent in a given time period, and it's modeled by this function. Okay? Notice that it's exactly the same, right, in terms of its general form, kb to the x. Y equals k times b to the x. But we'll see that there's something different about my k value, right? Here, my k value is greater than 0. Okay, what was the difference here? K value is still greater than 0. So nothing's changed as far as k value, but my b value changes. And my b value is a number that's greater than 0 but less than 1. Okay, give me an example of a number that's greater than 0 but less than 1. 1/2. That's a fraction. But it's a fraction and that's fine. It's a fraction, it's a positive fraction less than 1. Okay, does that make sense? So 1/3, 1/2, 1/4, 3/4, right? 5/16 are all examples of fractions that would work for b, but they're going to give me an exponential decay. Okay, so that's your difference. You look back over here, whenever I'm increasing, my b value is anything that's greater than 1. Okay, and it's going to cause it to have exponential growth. Down here, if it's less than 1 and it has to be greater than 0, it's going to decay. So if it's a fraction or decimal less than 1. Okay, so 1.1, if b is 1.1, is that growth or decay? Growth, because it's greater than 1. If it's 0.99, is it growth or decay? Decay, because it's less than 1. Does this make sense so far? We can identify growth and decay based upon equations. Okay, now we're going to get into something called natural logarithm. Okay, the natural logarithm of a positive number x is the power to which e, and you can find e in your calculator. Everybody's in here got a graphing calculator they can look at. Okay, let me pull one up on the board so you can see it, and I can make note of it there too. Okay, you're going to see down here towards the bottom left. Made it disappear. Okay, let me pull it back up. All right, should be about there. You should see something called ln. Right? Do you guys see that? That means natural log or log natural. And you should see above it, up there it's in yellow, on my calculator here it's in blue, and it says e to the x. Do you guys see that? All right, that's the e that we're talking about. Okay, let's see, I don't know, we'll see if it does this or not, clear some things out. Huh? I don't know. No, we got, so this allows you to put in an exponent to e. Let's see. But natural log, ln, and e are opposites of each other. So, like if we had to balance an equation, right, how do we undo multiplication? Division. How do we undo addition? Subtract. How do we undo a square root? By squaring it. So everything, we have what we call inverse operations, or operations that undo other operations. E to the power of y equals x, then y is called the natural logarithm of x. The abbreviation is y equals ln x. What I want you to know is that when solving an equation, natural log, or ln, and e undo each other. Is there something wrong? Yeah, there's water on the floor. There's water on the floor? Oh, okay, so we'll worry about that in a second. Okay, if you want to start cleaning that up now, I don't know if I've got a handful of paper towels. I just want to record this, make sure everybody knows. John Ray peed all over the floor. He's got to clean it up now. He says it's water from his water bottle, but nobody believes him. It's really embarrassing. He's going to have to go get some new pants. Okay. All right. So if you look, one of the things I want you to make note of whenever trying to solve some of these questions that you're going to get in your homework assignment is that you want to look at the examples, okay? And not just look at them, but look at how they solve them and look at the steps by which they solve, especially where it concerns natural log and E problems, okay? You're going to have to use a graphing calculator for these. So if you look at example on page 408, you see some of this, but you're going to need to go through the examples from this lesson closely to be able to understand those practice set questions, okay? And that's, tomorrow whenever we're grading this, we're going to go through probably, if I'm looking at, this is what, lesson 57, I'm going to see something along the lines, and maybe some of your example numbers are a little different, but anything that's using, say, example 3, right? E uses example 3. F is example 4. You're going to need to look at those things, and it may take you some time to kind of decipher what's going on. Take it slow, take it one step at a time, okay? All right. Let's see if there's anything else involved. Nothing else here. I don't know if I have... Nope, I don't have a lesson 57 pulled up. Let me get that. We'll work out a couple of questions. That won't work. You doing all right, John? Getting it figured out? Okay. We'll get you some Depends or something. All right. Got all over Diego's stuff, which is gross. Okay. All right. Did you guys get this document sent to you, hopefully? All right. The function f of x equals 200 times 0.904x, where x is the time in years, models a declining feral cat population. We want to know how many cats are going to be in 6 years. This is fairly easy because all that we have to do is plug in 6 for x, right? So I'm just going into my calculator. I'm typing 200 parentheses 0.904 close parentheses to the 6th. All right, does that make sense? Did we get an answer? About 109. Okay, so we didn't have to do anything really special there, did we? Okay, they gave us all the information and we needed to be able to do that. Somebody want to scroll down to the bottom and check and see if that's our answer? It is. 109 works for that. Okay. All right, let's take another look at something. Now here we have E being used. Okay, but that's fine because we have an E function in our calculator. So the number of bacteria present in a culture after T minutes, okay, time is given as a function of bacteria equals 1,000 times E to the K, which is a constant, times T, which is our time. Okay, if there are 24 or 2,412 bacteria present after 4 minutes, we want to find K, so we want to be able to solve for K. All right, so we're going to replace B with 2412 equals 1,000 E to the K4, right? All right, so we want to isolate and solve for K, correct? Okay, so what's the first thing I could move to the other side? Anybody know? This is 1,000 times E to the K. I could divide by 1,000. Very good. I can divide by 1,000. Okay, divide by 1,000. What's 2,412 divided by 1,000? So 2.412 equals E K to the 4th. Okay. All right, let's see if I can remember. There's an example that looks really similar to this. All right, and I think that you find this, you find this on example 5 in your book. Do you guys have an example 5 in your ebook? And they show you something along the lines of like 200e to the negative 0.36t equals 50. They divide by that 200. And then so what you want to look at is you want to look about 3 steps down and see what it is that they do. How do they get rid of that e? Well, they find the natural log of 0 or of okay, what do they do? I'm trying to see here. Okay, so they find the natural log basically of both sides. So what we wind up with is whenever we find a natural log of this, this is canceled out. Okay, so I wind up with 4k here, but we're taking ln times 2.412. So ln 2.412 is allowing me to get rid of that e. Okay, so you guys have that function in your calculator, right? You're going to hit natural log. You don't have to hit a second. Right, natural log 2.412. What do you get? Okay, 0.880. 0.880. Okay, could we just leave it as 0.88? Okay, So we're saying 0.88 equals 4 times k. What do we do now? Divide by 4. Okay, what's 0.88 divided by 4? 0.22. Somebody check the answer key. Are we right there? Awesome. So 0.22, k equals 0.22 is my answer. It's B right there. Okay, do we understand that? This is really kind of one of those that I wanted you to see done, because you'll see some things like this. And if we used example 5 to solve that, then I'm trying to look through your sample questions, then you guys should know how to solve potentially G, because G uses the same example. Okay? All right, what time are we out of here? 10:11, I think. Okay. Are we good so far? Do we get this? Something we're going to struggle with? Like I said, use those examples to the best of your ability. Hold on. I want to see this savings account question, because I don't know if it gives you... Okay, so this would be more like example number 1 when we're talking about exponential growth. And we should have a specific equation for this. I don't know if it shows it to you here. We've learned about it in another class. Actually, I think it is in this class where we talked about this, where we said our account equals principal times 1 plus, what was it? It was rate over number of times compounded to the number of times compounded times t. I think that's the equation that we work with on this. Okay? Which, that makes this my b. This in parentheses is my b, right? My nt is my x. My p is my k. Does that make sense? All right? So a savings account earns interest at a rate of 4%. Okay? Yeah. So that 4%, we're going to make that a decimal, so that's going to be 0.04. Okay? So we got 0.04. Compounded semi-annually. So how many times a year does that mean if it's semi-annually? I believe it's twice a year, but I'm not... let's see, semi-annually. Somebody Google it. What does semi-annually mean? You can always use that. Twice a year. That's what I thought. Semi-annually and biannually. That's okay. So twice a year. So that 2 goes there. So we have 1. Okay. And so we're going to do 2 times there. And it says, let's see, if the account begins with a principal of $1,000, okay, what will be its value after 8 years? Okay. So we're going to set it up like that. Does that make sense? Okay, why don't you go ahead and try to work that out. Let's see if we get the right answer. Hopefully I've set that up right for you. Clickety-clack. $1,848. And how many cents? 84 cents. Okay. Scroll down to the bottom, see, is that right? 1848.84? It's not. When you did the same thing? Was 1,372 the right answer? Yeah. Okay. Do you know what you did differently? You put 100 instead of 1,000. Okay, what was the change on that, Diego? 0.78. Because I'm guessing because we're talking about money, we always want to have to the... Huh? Oh, 79? Okay. 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 Does that make sense? All right, and this to me shows like a really important principle to life, which is saving money, because Here, if you ever get to a point where you have $1,000 you don't need, and you can put it into an account that earns interest, and it's compounded, that means that every 6 months, what you have in there, that interest is applied, and now your interest is earning interest. Okay, so it's going to earn interest after 6 months. That's going to be put back into the account, and then at the end of the next 6 months, it's counting interest on the interest that it's already earned. Does that make sense? And that's how it's able to accrue what, just by being able to put $1,000 away and not touch it, this guy was able to actually make $372.79. His money made money, right? Because he had $1,000 that he could live without for 8 years. Does that make sense? So, and the more money that goes into that account, initially, the more money, the more interest it earns, right? The more time it's in there, the more interest it earns, which is how if you watch kind of like money market stuff, there's people right now that if you can ever get to the point where you've saved $1 million and you can put that into like a mutual fund, a person or a family can live comfortably just on the interest that $1 million earns. Meaning that they're not ever touching $1 million, they're living off the interest that it made. So some of that stuff is pretty neat, pretty cool to me.